In a communication system, when we received a signal from an antenna, then the strength of that signal is never be constant, it varies. Whether it is a wireless RF link, radar system, or even an optical communication channel, the signal level keeps changing due to distance, obstacles, movement, and environmental conditions. Sometimes the signal becomes very weak, and sometimes it suddenly becomes very strong. This wide variation creates a serious problem for the receiver circuitry, because electronic circuits are designed to operate efficiently only within a limited input range. Now imagine if a weak signal enters the receiver. In that case, we would want to amplify it as much as possible so that it becomes usable. But if a very strong signal comes in and we are still using high gain, the amplifier will saturate, causing distortion and loss of information. On the other hand, if we keep the gain low to handle strong signals, then weak signals may fall below the noise level and become impossible to detect. So, there is always a trade-off between handling weak and strong signals, and this is exactly where automatic gain control, or AGC, comes into play. AGC is essentially a smart technique used in electronic systems to automatically adjust the gain of an amplifier based on the strength of the incoming signal. It continuously monitors the signal level and dynamically increases or decreases the gain so that the output remains within an optimal range. In simple words, AGC makes sure that whether the input signal is weak or strong, the output stays stable and usable for further processing. If we look at the basic working principle, an AGC system typically consists of two main parts. The first is a detector, which measures the amplitude or power of the incoming signal. The second is a variable gain amplifier, whose gain is controlled according to the detected signal level. These two blocks form a closed-loop system, where the output is constantly fed back to control the gain, ensuring that the signal always fits within the desired range of the system. AGC is mostly implemented using analog techniques because of the high speed and wide bandwidth requirements in communication systems. It has been used since the early days of wireless communication, and even today it remains a fundamental building block in receivers. You will find AGC in applications like radio receivers, Wi-Fi systems, radar, sonar, and many other systems where signal strength can vary significantly. Another important aspect of AGC is how fast it responds to changes in signal level. This is defined by parameters known as attack time and decay time. If the system responds too slowly, it may not properly handle sudden changes in signal strength. But if it responds too quickly, it can introduce instability or unwanted fluctuations known as gain pumping. So, designing an AGC system is not just about controlling gain, but also about carefully balancing speed, stability, and performance. So overall, AGC plays a critical role in ensuring reliable signal reception by automatically adapting the system to changing signal conditions. It allows the receiver to make full use of its dynamic range, prevents distortion from strong signals, and ensures that weak signals are still detectable. In the next part, we will move from this basic understanding and start looking at a practical implementation using the AD8368, and see how these concepts are applied in real hardware design.